Hello everyone, my name is Jesus Bautista Villar, and in this video I am going to tell you a little bit about our last work titled Behavioral-Based Circular Formation Control for Robot Swarms. In this paper, we show how to coordinate a swarm of unicycle robots with constant but diverse speeds while they orbit the same path. As you can see, our proposed method creates defensive escorting behaviors that resemble a tornado schooling of fish. Our methodology guarantees no collision among the robots, no divergence from the target path, it's feasible in practice and fully distributed. To achieve this, we analyze a scalable solution rigorously combining three key elements: guiding vector fields, control barrier functions, and a scalable overtaking rule on the outside. CBFs are effective to avoid collisions, but literature only offers CBFs for robots that can brake. When robots are unable to brake and can only turn, standard CBFs might lead to conflicts. For instance, in this scenario, the relative velocity vector is confined between the two collision risk zones highlighted in red. Therefore, it is not clear where the blue robots should turn in order to avoid a collision with any of the green robots. Formally speaking, we have that the standard CBF QP problems might demand contradictory actions. Therefore, considering these relative dynamics, we split LGH of I so that G is fixed and non-collaborative. In other words, I have to do all the job to fulfill the safety condition of the CBF QP problem. The CBF that we propose is a collision cone CBF with an adaptive collision radius, which, as you can see in the simulation, facilitates smooth overtakings. On the other hand, we propose an overtaking rule that will be triggered when both of these conditions are met. Note that the first condition warns about collision risk between robots I and G, while the second one ensures overtaking from outside the path, as you can see in this simulation. Moreover, once the overtaking rule triggers, we show that LGH of I remains positive during the overtaking under the mild condition visualized in this picture. That is, the velocity vector direction of robot I should be inside the semicircle highlighted in blue. As you can see in this simulation, smooth overtakings helps to meet this mild condition. The key point of this overtaking rule is that it is scalable and fully distributed. Moreover, we show that if we combine it with this control law for robot I, then it enables to solve the CBF QP problem. Next, let me show you two interesting applications of our method. In this first scenario, we have a mothership launching 50 robots to orbit around an elliptical path. Note that once the last robot is launched at t equals 10, all variables stabilize, the safety distance is preserved, LGH remains positive during overtaking for all robots, all the overtakings are smooth, and the mild condition is fulfilled. In the second scenario, two teams of 50/50 robots travels in opposite directions. Let me note that the red robots do not know about the existence of the blue ones, so the blue team have to do all the job to avoid collisions. Moreover, since reds do not share information, blues have to consider an angular velocity omega greater than the angular velocity of every robot that they have to overtake. In that case, every blue robot consider omega equals 10. The initial spike in the omega data axis is due to the alignment with the GBF. But then you can see that all the overtakings are smooth and that the safety distance is preserved. Thank you so much for your attention.